So number 29, we have a crystal of cesium chloride, and the cesium ions form 8 corners of a cube, and the chlorine ion is at the center. The length edge of a cube is 0.4 nanometers. The cesium ions are each deficient by 1 electron and thus have a charge of positive E, and the chlorine ion has an excess electron, therefore a charge of negative E. A, what's the magnitude of the net electric force exerted on the chlorine ion by the 8 cesium ions at the corners of the cube? Solving this one, first of all, requires a lot of geometry, and this is probably why this is a 3-dot problem. So if I just look at the side that's closest to us, and we're trying to figure out the distance between the chlorine ion here and the cesium ion here, please realize it gets a little bit exciting. First of all, the distance from this to this front face, and again, remember, this is actually perpendicular to the face. It's right at the center of the face here. Is going to be half of this distance because we're halfway between the front and the back. And now here's the tricky part. What's the distance down from here to here? Well, some of you can see it probably immediately, but some of you might not be able to see it. The distance from the middle of this face down here would be 0.02 nanometers. And from here to here, it'd be 0.2 nanometers. So what's this distance? It's 0.2 times root 2 nanometers. And so you can actually solve it like that. That's not what we're actually trying to find, though. We're trying to find the distance between the chlorine and the cesium ions. And to do that, we have to use Pythagorean theorem one last time with those two, or with the two dark blue sides. And we'll discover that that side there is 0.0346 nanometers to 3 sig figs. Now we can actually use Coulomb's law to solve the forces. If we use Coulomb's law, and I have it written as, instead of K, as I wrote it as 1 over 4 pi epsilon naught, times Q1 times Q2 over the distance between them squared. Please notice this is the magnitude of the force. I'm not going ahead and putting in the r hat for a vector. If we plug in our numbers, the charges on both of these are the charge electron, the distance between them. This is that same 0.346 nanometers converted into meters. And if we solve it, then we get this force. So that's the force of attraction between the chlorine ion and the cesium ion. And yes, it's also the force of attraction between the cesium and the chlorine drawn the other way, but I just want to draw that. So now we can answer the question, what is the net electrostatic force? Well, there's one little trick on this one. We also have the same force towards the cesium ion at the other corner. And if you haven't quite realized it yet, because this thing's symmetric, we have the same force this way towards this one as we have towards this one. And then we have the same force towards, I can't really draw it, this one as we have towards this one. What is the net electrostatic force? The answer is, believe it or not, 0. You're like, wait, you made us do all that geometry? Well, here's where the interesting part comes in. Part B. If one of the cesium ions is missing, the crystal is said to have a defect. What's the magnitude of the net electrostatic force exerted on the chlorine ion by the 7 remaining ones? In that case, we end up with this. So let me take out that top corner. What does that do? It immediately removes that force. Now, all the other ones are balanced, but now we have this unbalanced force, and that is going to be now the net force on the chlorine ion, and it is going to be exactly that, assuming that the crystal doesn't change its geometry. So the answer to A, 0. The answer to B, 1.92 times 10 to the minus 7 newtons. I hope that this helps.